A little bit early. I probably should have spent this time preparing a little bit better, but it'll do. Now, what am I going to be talking about today? Today so yesterday I finished Scope of the Profession and Historical and Societal Influences. What we're looking at today is, we've already discussed orders of levers, and I've set that for us for classwork. Orders of levers. So really that should be 4 at this point, because that's set work. I've had a due date. I need to really start recording those people who haven't finished things. I might use some of my time on Friday to go and check up on homework. But in the meantime, I'll just actually grab this tab out. So orders of levers. So we've learned that there are 3 different orders or classes of levers. So we generally talk about seesaws, wheelbarrows, and fishing rods. Obviously, there's a whole bunch of other applications. So things like hammers are the same as a seesaw, and we have second order levers are things like a nutcracker, and then third order levers are things like tweezers or tongs. But what we're going to go into in a little bit more detail than we have in the past is efficiency, mechanical advantage, and velocity ratio. So I've got some videos on some of the harder questions here. I'm going to go through the easier questions. We'll go through the textbook a little bit as well, and that's what we're going to do this morning. Then after that should be what we effectively cover today. Then after that, we've already talked about forming methods. Specifically, describe the forming processes used in biomedical engineering. That's part of your report, so I'm not concerned about that. Compare the macrostructure and microstructure properties of materials. Now, that's something I probably need to talk about. So we need to say, draw some cast objects. I'm going to go through that. I haven't set the casting video for homework yet, and that was one of my plans. So I'm going to try and I'll set the casting video for work, and then cutting. Okay, so we've set cutting for homework. I'm pretty sure, or I certainly have talked about it. If I haven't, I've talked about what page the details are on in my homework video. Just getting a lot of notifications, so I'm just checking. Yeah, it's fine. So cutting, I need to talk about. I mean, I've talked about it in a video, but I probably should set it for homework. Explain the appropriate. Explain properties and uses appropriate to biomedical engineering materials. We've done that for home. That's done as part of the engineering report. Now, titanium, I have set. Well, I happen to click the right thing. So titanium I've set for homework. A student asked me, is it 100 words for each, or is it 100 words total? I think I would be impressed if someone could write down 100 words to explain this. If they just said titanium is, and then colon, and then just wrote bullet points, moderately hard, or moderately tough, has more. I mean, these are things where it's harder for us to look at. So okay, in terms of toughness, elasticity. Let's have a look. So titanium is fracture toughness of titanium is 28 to 108, whereas compared to steel, whoops. Okay, so how we're going to look at it is maybe this curve will give us an idea of the relative toughness of titanium. So we know that toughness is the area under the curve. And wow, that was some trippy stuff that it's the way it was scrolling there. So generally we can say that most metals have a reasonably high toughness, right? So what we can do is we can compare the toughness of, say, of titanium to steel. Steel is a good benchmark, where if we're looking at the stress strain curves, where we wanted to stress strain this is where we want to say, so titanium probably has less toughness than steel, but only a little bit. The area under these curves is probably pretty close. And so we can say that we would say steel has good toughness, so we would say that titanium by comparison also has good toughness. So because it's got a similar area under the curve. And that would be the justification. If you're writing that in all of this in less than 100 words, then that's fine. But that would be the argument I'd make for titanium. In terms of hardness, so titanium using the Mohs hardness scale, right? So we would say that, well, obviously diamond, it's the Mohs hardness scale. I think I said Mohs. That's a thing I know that I get wrong. This is not a linear scale, right? So diamond is like, I don't want to say, I know that diamond is twice as hard using something like the Brinell's test as something that's rated 9. So tungsten, it's substantially harder than tungsten. Ceramics can be anything from concrete, brick, and also sand. Pocket sand is the thing that scratches the screen of your things. Okay, so we can see titanium has substantially higher toughness than stainless steel, or it doesn't just have steel because steel is a range, but we would expect that steel has a hardness of about 5, maybe 5.5 for like tool steel. And glass is in this sort of 5 to 6 range. So it's titanium is harder than tool steel, but if we just go to mild steel or Gorilla Glass, right, as an example. Okay, so Gorilla Glass has not been really expected to have a toughness of 5. Hardness is not toughness, Greg. Yeah, I don't like it saying around 7, just because that's for... it's not released is the reason. But we're talking about Galaxy S4, so this is really old. Okay, yeah. In that case, I'm more inclined to say, I don't even know which Gorilla Glass that is. Okay. The point is, in my other video on brakes, I talk a lot about different hardnesses and talk about how, like, we looked at the chocolate that's harder than steel, and we've said steel can really range. The hardness of mild steel is very different to the hardness of tool steel. But we can see that value of 6 is fine. Now, I don't really like Mohs hardness, but the thing is, it's so apparent to people. It makes a lot of sense that it's easy for us to relate to. But so here we have steel as being like, so mild steel might be as low as 4. No, I do not want that. I think I clicked that twice. Okay, here we go. This is exactly what I'm looking for. So it's a knife and glass both about 5.5. So if we're saying that titanium is higher than that at 6, I think that it's nice to, I say it's a moderately hard, and that's what I generally consider steel and glass to both to be moderately hard. It's slightly higher than that. It's less hard than a nail. So I think moderately hard is fine, but it's better if you say its hardness is roughly equal to steel, to hardened steel, something like that, to high carbon steel, something like that would probably be good. It gives a reference point, so we're saying how hard it is relative to other things. It's not as hard as a drill bit, a masonry drill bit, but it's harder than your standard mild steel glass. It's harder than mild steel or glass. That would be my answer for titanium there. So the point is, if you said titanium is, hardness Mohs 6, toughness approximately equal to steel, slightly equal to or slightly less than steel, elasticity, the same sort of thing. It's slightly less elastic than steel. Its strength is approximately equal to steel. Its specific strength, its strength to weight ratio is higher than steel because it's lighter, right? If you did that, you could probably get it done in 100 words. The point is that it doesn't need to be many words. Okay, going back to, I really went down a rabbit hole there. Sorry about that. Bring things back. Okay, so for titanium, we've spoken about. In terms of alloy steels, we've done a whole thing on alloy steels. Now, when I did my Zoom classes the other day, I made sure that my students were aware of that. But I'll just show you what I mean. Here we go. I happen to have it open. The ferrous metals document is, I was going to put a picture on this, but I didn't. You should be familiar with this document. We went through it just before our exam period, assessment period. It's this document here. There's a video that explains the entire document that goes through it. And that covers our alloys, steel alloys, that covers cast iron, and it casts stainless steel. So all of that should be there, or it is there. So we've covered that. So I can now say that we've done titanium because I've said that work. So what we haven't done yet is, so what my goal for the next 50 minutes is, we're going to just cover orders of levers just a little bit more, just so I can tick that off as 4. I'm going to tick it off as 4 now because we're going to cover it next, and I know that we've talked about it. We're going to talk about mechanical advantage in some detail. I'm going to set casting homework, which I haven't done yet. That will be due. I'm going to make that due on Friday because I've already got something else. I've got the efficiency is also due on Friday. So I think setting 2 things for Friday is fine. When is the biomedical report? It's also due on Friday. Now it looks like a lot of work, but you've been given, I set that biomedical work weeks ago, and the biomedical report weeks ago. I've pretty much given you the answers. I've given you a sample document. I've gone through it. If you would even scroll through the video, you could just literally copy the text I've written. And I'm giving you more than a week to do this work. So I'm setting a lot of work into the future so that, anyway, so casting will also be due on Friday. I'm thinking I could make it Monday, but if I see something on the chat before I finish that asks me to make it Monday, I'll make it Monday. That's my deal. So casting is going to be homework, and then polymers and ceramics, we'll talk about that very quickly. It's important to say that this is effectively covered already in the engineering report. We talk about polymers and ceramics. We talk about in the application of, let's bring up the sample report that I have, and we'll talk about it there. So just to give people another opportunity to see. Now, the sample report that I've given you, I've used lorem ipsums. So lorem ipsum is placeholder text. It looks like Latin, but it's just is this? Great. Okay, so in the document I've given you, you can see it just says lorem ipsum over and over again. So I expect you to talk about alumina and zirconia and where they're used. Zirconia, I've actually given you the text because I wanted to reduce the amount of work you had to do. So I've given you the work for zirconia, and for polymers we have here ultra high weight, high molecular weight polyethylene. Just to show you the actual text here, so we talk about alumina. Alumina is a combination. I would say it's a compound of aluminium and oxygen, but you know what, that's okay. I'm using someone else's text. It is more it is a naturally bioinert material. It has good compressive strength, high wear resistance. In terms of disadvantages, it has limited tensile strength. It can fracture, but this is counteracted by infusing the alumina with zirconium to increase strength and stability. It has a cost about this. Now, where are we using it? Okay, so the acetabular component is made of titanium. The liner is made of polyethylene. The femoral head is made out of zirconium infused alumina to increase strength. So that the ball is going to be made out of alumina, made out of ceramics. So that text I'll leave on the screen for 10 seconds. Gives you a relatively good idea of the sort of standard I'm looking for the report. And when we're talking about materials, that's an application of the research that you can have when we're talking about polymers and ceramics. So the liner is going to be made out of polymer, the ball is made out of ceramic, and in this report you'll discuss its properties and why we use that. So I don't think I need to set that for any specific work. So I think that given that I've set the homework, we can say that we're going to talk about it I just want to go through the textbook. That's the last thing I'll do. So to tick that off as 4. Okay. So we've looked at what we're going to do. We're going to go through orders of levers again quickly once. We're then going to talk about mechanical advantage. We'll read through the textbook on that. We're going to talk about the casting. I'm going to set casting as homework. And then mostly I'm going to expect you to watch a video on that because I've got a video I'm quite happy with. And then polymers and ceramics we're going to talk about. So that's what we're setting for today. I'm going to set this as 3 just to remind myself before I go that that's what I need to do. Okay, so with that said, let's talk about levers. What I want is the textbook, which I should have open, but I don't. Nope. Okay. So we're using Engineering Studies, the Definitive Guide, Volume 1, Edition 2, maybe. I think it's the 2nd edition. We're looking at Chapter 4, which is Biomedical Engineering, and we are going to be we're starting with mechanical advantage. So first of all, we need to know that there are 3 orders or classes of levers. I've already mentioned these before, that we have the seesaw, the wheelbarrow, and the fishing rod. Class 1, 2, and 3. How we can define these is a seesaw, the load and effort are on either side. With a wheelbarrow, the load is next to the wheel, or the fulcrum. And with a fishing rod, the load is way out far. Now, it's important to notice that there's something called mechanical advantage. If you're not familiar with mechanical advantage, what you can do is you can go back and watch Now, I will have shown this to us already, but it probably wouldn't hurt for me to include this as a link. I'm not going to watch it now, but I'm going to include this as a link in the course. And I'm just going to make a quick comment about it as well. Nope. You know what? I'm going to leave it open so while I post it in the window. Okay, so in this video, what is the knowledge that you need to know? So they have the story so far, which I think is quite useful. Machines don't reduce the energy you need to move things, but they can reduce the force needed. Often we also talk about machines as using things like chemical energy, right? That's another use. But when we're talking about simple machines, they don't change the energy, they change the force required. They do this by increasing the distance through which you exert the force. So they give you a force amplification or a mechanical advantage. The two simplest are the inclined plane and the lever. The principle of the lever states the longer the arm of the lever of which the force is applied, the less the force need be. So that's the position that they've established. And what they've shown is that a lever, if you have a lever that's 4 times longer on one side, right, you're going to get 4 times the mechanical advantage. That's the idea. So they're going to show you how you can calculate what the mechanical advantage is by saying, well, in this case, it's 4 times, we're getting 4 times the force out of this lever because it's 4 times as long. Now, that relationship is efficiency. So they don't really talk about this. They talk about the mechanical advantage, and they've said the mechanical advantage is 4, but this guy's going to use a ramp, and his thing is his should be 4. He predicts that he has a mechanical advantage of 4, but he doesn't get mechanical advantage of 4. He actually only gets a mechanical advantage of 3, and the reason for that is friction, right? And so friction makes the lever more effective. Then it says, hey, friction's important, don't worry. Now, the thing is, it explains the difference between friction and velocity ratio, but what we need to worry about is this thing's exciting. Mini motorways. Okay. Okay. Wait, I wanted that there. Okay. Sorry about that. I did want that there because this is the right size for my OBS. I forget these things sometimes. Okay, there we go. So that's our starting premise for, and we just went through that really, really quickly. What I was going to do is, my intention was to quickly post that into, I might as well have you watching this at the same time. Sometimes it can be really annoying dealing with Google Classroom. It doesn't behave the way you would like it to. Just adding an extra link in. Did that happen? Did that go? Didn't look like it. Okay. We also expect you to know the efficiency of pulleys. So I know that I've covered that in a lot of detail on Facebook. Let me show you where I've talked about that on Facebook. That's not a bad place for us to be. So titanium, we do want titanium, but we want titanium images. I did want to leave that open actually. Oh. Stop trying. I had a former student asking for some advice about uni stuff, which was really getting outside my my expertise anymore, which is a shame. But for maybe first year uni, I can maybe still give you a hand. What I'm looking for is stuff on mechanical advantage and pulleys, which we talk about way back early. So here we can see our pulleys, here we can see our levers. So we talk about, so here we have a video on the lever, and we can, those videos aren't really all that useful, but in terms of engineering applications, so the thing we often see is things like forceps, that forceps can, depending on if we want reach or not, these typically have a mechanical advantage greater than 1, but it's worth knowing that third order levers, I think by definition, always have to have a mechanical advantage less than 1. So the question is, why would you ever want to have a mechanical advantage less than 1? And the answer is because tweezers and fishing rods and tongs, they all give you not mechanical advantage, but what they give you is control or reach or something like that. So in terms of pulleys, you need to know that there are questions on mechanical advantages of pulleys, and that's what these notes relate to. I might link that stuff in to Google Classroom later if I remember, but for the moment, what we're focusing on is what the textbook talks about. So now that we've got that, I'm going to leave this open actually and just duplicate the tab and bring it back, so that way I've got a reminder to set myself some work for later. Okay, so now that we've gone through that, we can get the textbook, which should be open here. And okay, what are they going to say? So we know that there are different kinds of levers. So we use things like retractors in surgery. So these are things that that we can use to take stuff, or to move things, to when we're doing surgery, when we want to position things or hold things, we use these sorts of tools, right? Now the question is whether or not these things are going to give a mechanical advantages or not. That's what we're here to find out. Okay. I might even include that as a thing into our documents as well. So first order, second order, third order, I've now discussed that several times. I think we've revised that sufficiently. What we saw in the Eureka video is that mechanical advantage is equal to load over effort. That is given to you in the HSC formula sheets. So if I just go... It's funny that one, the 2020 paper, they never just link. And there's a space missing. Okay, so here they give us these formulas in the formula sheet. They say mechanical advantage is equal to L over E. Velocity ratio is the distance of E divided by the distance of L. So this is load over effort. And that eta, this is the Greek letter eta, is equal to mechanical advantage over velocity ratio. So mechanical advantage equals, so male is pretty apparent. Most people remember that formula even without the formula sheet. The rest of it's given to you, so it's important to remember that we can't really have an efficiency. We can't have a machine that's 110% efficient. So people might talk about that they might have their engine running at 110% capacity or something like that. What they're talking about there is not that the machine is producing mechanical advantage greater than the velocity ratio. What they're talking about there is that a machine will be rated at a safe operating level, and this is not in terms of just like actually injuring people and causing harm, but also harm to the machine, so that the machine might start being more likely to behave outside its tolerance range, might start having unacceptable levels of wear if you're overclocking, if you're making the machine operate at more than 110%. Because the efficiency of the machine, so the mechanical advantage has to always be less than velocity ratio, which means that our efficiency is always going to be a percentage, a number between 1 and 0, right? Or between 0 and 100%. That's what we're looking at to start off with. We're going back to the textbook. Okay. You know what? I'm going to drag this into here because that's not for you, but it is useful and I don't want to keep having to look at a tab. So the velocity ratio is when we make a prediction of how the velocity ratio of that lever or that inclined plane, we saw that the two professors, Professor A and Professor B, they both expected that their machine should have the same level of efficiency. They both predicted that both their machines would have the same mechanical advantage when we watched that Eureka video. Let me just open that up again.
straight up. So he...
Okay, so in this case, we're measuring, the value that we measure is the mechanical advantage. I like to think that the mechanical advantage is a measured value or a measured attribute. You might think, why would I say a measured attribute? Well, measured attribute is MA, mechanical advantage. Whereas on the other hand, we made a prediction beforehand. We said, well, the ratio of these things is 4:1. So we predicted that we get a mechanical advantage of 4:1, or 4/1, so a mechanical advantage of 4. And the reason for that is because levers are really efficient, right? They have efficiency close to 100%, which means that we can expect the mechanical advantage and the velocity ratio to be equal. But when we're comparing these distances, what we're actually looking at is a velocity ratio, right? Sometimes called IMA, right? Worth mentioning here, VRIMA. Bing. Okay, so like I said, we've got these mechanical advantage videos. We've already got those in Khan Academy, but the actual mechanical advantage versus the ideal mechanical advantage, right? Okay. We don't use the term IMA and AMA. We don't use those terms. Instead, we use mechanical advantage and velocity ratio. So I like to think of the velocity ratio as an unachievable ideal, right? It can't be achieved in real life. I think I just closed the window. It can't be achieved in real life. Instead, we can only have something that approaches that value, right? So the velocity ratio is a virtual thing, right? So we've talked about what are they called? It's band Jamiroquai a couple of times in class. So mechanical advantage is the output force over the input force, or the load over the effort. So it can be useful to think of it this way, but generally you're just trying to think of the load is the thing that we're lifting, and the effort is where the engine or the human is being applied, right? Now, this professor, he has a ramp that is 10 high and 40 centimeters long. He expects that he should have the same velocity ratio. Let's have a look. I just want to see him measure. Okay, so he expects that he should have the same. He has the same velocity ratio, but he doesn't get the same mechanical advantage, and that's because the ramp is less, or the incline plane is less efficient, right? It has an efficiency in this case of 75%, and that's because of friction. I once had a student who was a Jehovah's Witness who couldn't watch that part because they have the demon friction. So be warned, religious people who might be affronted by this, but see, the demon of friction. But they also talk about how friction is really important. We talked about this when we talked about brakes, that friction is important for allowing brakes to work. And also we need friction in order to transfer the engine, the force of the engine onto the wheels. If the wheels slip, right, that's what happens when you get bogged. So friction is both good and bad. So I think that's a fairly in-depth overview of friction, and that should give you a pretty good idea of where we're going with this. What we're now going to look at is specific examples and work through them. So we've now talked about mechanical advantage equals load over effort. Load is the thing we're lifting. Effort is where the engine or the human is being applied. The velocity ratio is the distance traveled by the effort versus the distance traveled by the load. So in the case of the ramp, we could see that we were lifting the object up 10 centimeters into the air. That was the distance traveled by the load, whereas the effort was being stretched out over a longer distance. It was being stretched over 40 centimeters. And in the case of the lever, just to bring that back again, we can see that the measurements of the mechanical advantage. So the distance traveled is 10 centimeters, right? That's the distance traveled by the load. The load is the book. Whereas here we can see the measurement, that in order to make that book go up 10 centimeters, well, we're rotating the book 20 centimeters, and we're rotating it 20 centimeters by rotating the effort 80 centimeters. So we're rotating four times as far. That's what we've got to think about when we talk about velocity ratio. We think about velocity ratio is measured in it's a unitless number, but here we have distances measured in meters, a meter divided by a meter, whereas mechanical advantages are measured in newtons. These are what measured in reality, measured attribute. Okay, so that's why I keep disappearing, because it's smaller. There's no good overlap. Okay, so once we have that that concept down, what we then want to do is we want to look at the efficiency. So efficiency is mechanical advantage divided by velocity ratio times 100. Now, I don't think that, near adults, people in year 11 or almost year 12, shouldn't have to have the times 100 aspect explained to you. And you'll notice that there's no times 100 here, right? The number is going to be a number between 0 and 1, and numbers between 0 and 1 are often expressed as percentages because it's a little bit more, easy to picture. Okay, so we've talked about the three orders of levers and what are their applications. So the first order lever, the mechanical advantage may be greater than 1 or less than 1 depending on the distances. A second order lever always has a mechanical advantage greater than 1. A third order lever always has a mechanical advantage less than 1. Right? So that helps us to, we talk about how, so seesaws, way back when we first talked about these, I talked about how fat kids always win on seesaw. It all depends. If the fat kid is sitting further or is sitting closer, a skinnier kid might still be able to win at seesaw. In the case of the wheelbarrow, a wheelbarrow is always going to give us advantage because the distance traveled by the effort is always greater than the distance traveled by the load. In the case of third order levers, it's the other way around. So here we have, now if this was a classroom environment, I'd say, what kind of order of lever is this? But it's because we have the fulcrum in the middle, and we can see in this diagram here, we have a free body diagram here, that because the forces are parallel, are mirrored, we can just simplify it into just one set of forces. So the scissors becomes this free body diagram. It's not scissors. I think that they're calling it forceps, not a retractor. Now, we can determine straight away that because the fulcrum exists here at point P, it's in the middle. It's going to be a first order lever. Now the question is whether or not it's going to give us a positive or negative mechanical advantage. So what we can do is we can look at the velocity. I just said that we can determine its mechanical advantage. We said mechanical advantages are a measured attribute. We don't have a measurement of the effort required. What we're doing is we're assuming that it's 100% efficient. So if we're assuming it's 100% efficient, what we can do is we can calculate the mechanical advantage by saying mechanical advantage equals the velocity ratio. I wish that Copeland said that in this book. He doesn't, so we just have to accept that at this point. Now, the mechanical advantage here, or the velocity ratio, we're saying that the load is traveling 90 millimeters and the effort is traveling 70. So we have the load is traveling 90 and the effort is traveling 50. If that's the case, that means a mechanical advantage, a velocity ratio rather, is going to equal 5 over 9. 5 over 9 is 55%, repeating of course, and the mechanical advantage is going to equal the same. It's also going to equal 0.55. Now, if we know the load that's being applied, well, what we can do is we can apply that velocity ratio here. I think Copeland may have made an error. Oh, no, that's fine. That's fine. I take that back. I was blunder on my part. Sorry. I was worried that the units, because it's, I thought this was 60 and not 50. Okay, so we're doing things measured in meters, and that's fine. And we haven't calculated out the mechanical advantage, but we'll see if my method works. So I said that 5 over 9, 5 divided by 9 equals 55%. These days, because I've gone through this book enough times, I have a pretty good idea of where there are mistakes, and like there are errata here and there, but I was surprised to see one there, but anyway, let's go through it. Now, we're expecting that, I know that it's the mechanical advantage is, so 55, the velocity ratio is 55%, which means mechanical advantage is 55%. What that means is that if that's the case, our effort is going to have to be greater than our load, because if our mechanical advantage was 1, if the mechanical advantage is 1, then they would be equal. If the mechanical advantage was 2, it would mean we'd need less effort. If the mechanical advantage is less than 1, it means we need more effort. How much more effort? Well, we're going to do, what can we do with 0.55 to make it go, to make the number bigger? We divide by 0.55. So we say 60 divided by 0.55, repeating, gives me 109, which is the same as what Copeland has here. I'm not going to write, if I was in class, I'd write that on the board, but I'm not going to write that in paint because I'd just be ugly and messy and take forever. But you can see that they've calculated the mechanical advantage as equaling 0.555, rounding up to 6. The point here is, I don't like that they've taken this specific approach. We've assumed that the thing is, we've made an assumption here, that because we didn't know what the effort was, right? We said that in order to be in equilibrium, this is the case, but that's because we're not including an unknown force of friction. So anyway, they've worked out the... Now, when we're talking about the velocity ratio, you'll notice that what we're actually doing is these things are not traveling. When we say that it's rotating 90 millimeters compared to rotating 50 millimeters, what it's actually doing is it's actually rotating in a circle around P. Now, if we rotate it in a circle around P, what we have is 2 pi r divided by 2 pi r, right? Because we're not given diameters, we're given radiuses. But in this case, those 2 pi's and r's, they cancel out. Right, so the 2 pi's cancel out, leaving just the r's. Because if they've got 2 pi on top and 2 pi on bottom, those things cancel out, which we can see here. So we really are concerned about it traveling in a circle, and that's important for when we look at more complicated questions. Okay. Now, it says to us, if the efficiency of the 4 steps was 85%, what would we calculate the mechanical advantage? Well, okay, so we said that the velocity ratio is 0.56. If we said that it was only 85% efficient, what we do is 85% times 0.56 will give us 0.47. Now, there's a little comment here that Copeland wants to draw to our attention. Since VR is constant regardless of efficiency, whether the efficiency is below 100%, the same value was used as the previous example. Yeah, that's fine. So what they're saying here is that the efficiency is the efficiency. It doesn't matter if it's above 1 or less than 1. We just multiply the efficiency. And that's what we see here. This is the equation, right? That if we want to calculate mechanical advantage, what we can do is we say mechanical advantage is equal to, we move this, we multiply both sides by VR, so we get efficiency times velocity ratio equals mechanical advantage, which is exactly what we said here. Mechanical advantage equals efficiency times VR. Once we know that, we can then take 60 divided by 0.47 gives us 126. Happy with that. It talks about the human structure as a machine. We've discussed this a little bit in other videos, but I'm happy for you to read this. Maybe we'll set that for homework and talk about the maybe I'll actually adjust this homework. Is there anyone who's already submitted this work? It's not there, not there. Zero. Perfect, which means I can adjust it. Okay. I've already said you had to read it, answer the chapter review questions. I might just say I'll create... no. You know what? Why does this not have the Eureka stuff in here? Huh. The Eureka stuff didn't save. what I'm typing is I've decided to make it an extension. If I could add in a document for you to type your answers into, I would, but I've already made you answer questions. Extension. I'll give you 2 parts of extension. Biodynamics. Oh, okay. Biodynamics is not the same thing as biomechanics. Okay. That would have been funny. I'm glad that I checked. Okay, so biomechanics. So dynamics is generally what we call moving forces, right? As a civil engineer, I only ever learned statics, right? I never learned dynamics. There is this thing called biodynamics, which is hilarious, right? It's all about burying. So what you do is, if you want your wine to taste good, what some people think you need to do is you need to take a cow's horn or an ox horn and fill it with like blood and manure, and then you bury it under the full moon, and now you know, it'll make your plants taste better and stuff. I'm glad I caught that, because that would have been embarrassing if let's see if I can find someone burying a horn. I know you do something with a horn, and like, sometimes I think, how do I even know this? Yeah, so there you go. Anyway, leave that for something exciting for you guys to look up. Whereas biodynamics and movement, what are the 3 key principles of biomechanics? There we go. That might be, we'll copy that, and that's, no, that's too hard for you. Anyway, I'll chuck in something about 2. Didn't spell that right. Biomechanics, not dynamics. So it means the same thing. Like dynamic forces mean moving forces. Mechanics can be static or dynamic. I don't think that's too advanced for you, but that'll do as extension. Because there are some people who don't have enough work, presumably. Okay, so back to our textbook. Okay, so we've gone through the book. We have to obviously make. So how does this relate to biomedical innovation, right? Or biomedical engineering. Well, obviously we're going to use things like forceps, and we're going to look at bikes. So exercise bikes is a question, but it's also important that we make sure that our devices have sufficient strength, that they can apply their forces appropriately. But we also need to think about like the human structure, which is that when we use our muscles, we use our arms for leverage, right? That's something that we need to consider, that we don't want to apply forces in such a way that they're going to create problems in the long term. So the problem with early hip replacements is that they can change the way that people move because they distribute their forces in a different way. And when they distribute their forces unevenly, that can create chronic illness down the road. So that's a concern that we want to look at. Okay. So what we're going to do is we're going to just quickly mention these homework questions. I'm not going to do them for you because that would defeat the purpose of having these questions. But here we go. We've got mechanical advantage has a set of forceps, has a load of 25 and an effort of 20. Well, mechanical advantage equals load over effort. So 25 divided by 20, that's a pretty easy calculation to do, right? 1.25. I said I wasn't going to give you the answer. Question 9, we're just literally copying the thing above, but we've got the velocity ratio. The effort is going to be applied by the human or the machine, right? Like when the engine. So that's going to be the velocity ratio equals distance of the effort divided by distance of the load. So the distance of the effort in this case is 75. We're just going to use everything in millimeters. We're not going to convert it to meters, but it would be 0.75. And but the different distance, if it's divided by the distance of load divided by 120, it's going to be a number less than 1. Now, this question 10 is quite difficult. So how this question 10 works is that we need to compare the, for the moment, let's just think about comparing the mechanical advantage is pretty easy. The human or the engine is the effort. The load is going to be this force here, right? So our human has applied, presumably, right? It could be a chimpanzee or something, but let's say our human is applying 440 newtons to turn this wheel, right? Our human is turning this wheel. Now, that's our effort, and our load is 74. So we can work out the mechanical advantage pretty easily. Mechanical advantage equals load over effort. 440 divided by 78 gives us our mechanical advantage. To calculate our efficiency, though, what we're going to need to do is we're going to need to compare the distance traveled by the big wheel, right, which is our load, compared to the distance traveled by the pedal. Now, to do this, we need to know that the wheel is going to spin around, right? So let's imagine if this thing turns, right? It's got 17 teeth. So by the time it's turned 17 teeth, this thing has moved about a little bit more than a third, or I think it's a third. We can just look at that ratio, just get a calculator, and we can say, well, 50 divided by 17, right? Yeah, it's pretty close to 3. So by the time this has gone 17 teeth, it's turned around 17 teeth, this wheel has only turned 1/3 of the way, right? So we go 17 teeth, and then we go another 17 teeth, that's 34 teeth, and this has now gone, so it's gone around the thing twice, but this has only gone 34 teeth out of 50, so it's gone around 2/3 of the time. By the time it goes another 17 teeth, this time it's going to be, what, 51 teeth, right? By the time it's gone 51 teeth, this has done a full rotation. So if we're comparing the distance traveled, well, now a reminder that we can add the pi into this, right? They've got the diameter here, but we could multiply both of these things by pi, but we could just compare the diameters and just compare the number. Well, you know what we will? We will actually, I hate to include pi because both sides divide by pi. Right? So if we say the mechanical advantage, so we're talking about velocity ratio. So mechanical advantage is load over effort. So velocity ratio is going to be distance of the effort divided by the load. All right. Okay. The pedal, we know it's only going to rotate once, right? Once, we're going to measure but once per rotation of the pedal. Now it is going to travel. Its rotation is going to be 2 times pi times r. All right, that's a terrible r. Whereas the other one is going to go 2 times pi times big R, but also times something called nrev. Now, if we were in class, I might play a song by Mercury Rev called Holes, dug by little moles, but you know, I can't do that sort of stuff on the stream because otherwise they'll take my stream down. Okay, so what are the distances here? The nrev, we said was, we'll get to that. Okay, so what we're going to do, I'm just going to cross out pi because I don't like you, pi. You're irrational, right? And I'm going to cross out, no, I need the 2. I need the 2, right? And the reason for that is because they haven't given us the radius here. They've given us diameter. So what we're going to say now is we've got 2 times 170 divided by 622, which is 2 times the radius, also known as the diameter of the big wheel. But we know that the big wheel is going to turn around, right? Big wheel keeps on turning, rolling on the river, like not on the river. Okay, it's going to turn around 2.94 times for every rotation of the pedal. If you calculate that out, so we get 340 divided by, well, first we'll do multiply by 622, and then if we, so we'll call that 1829. So we've got 340 divided by 1829 equals 0. Now with these sorts of questions, we want to write our VR, we want to use 4 decimal places, right? That's the rule. We use, for byte questions, we use 4 decimal places. Now I have included for you videos of me solving a whole bunch of these questions, and I will include the work onto the chat, so a whole bunch of HSC questions with answers. Okay, we're coming up in an hour. I didn't cover some of the stuff I wanted to talk about so casting, let's just quickly go through. I might go a little bit over my time, but it's a recording, so if you don't have time to watch it now, I think we wouldn't be going to assembly now, so no one's got class that they're going to. So I'm going to push a little bit longer and just go through this. So would it make sense to make this a separate recording? It would. That would be smarter, except I've already said what I'm going to do in the recording, which is always a worry when I do these sorts of things. It's hard to necessarily, because I don't have the experience of teaching online nearly as much as I do in the classroom, it's not always easy to get these things perfectly timed. Okay, but also I want to set up Wednesday for discussion questions. So, okay. Forging. At this point, we've discussed more than once about, I talked about this in some detail in our Zoom lessons last, that to make sure that students were aware, they understood what was going on, that when we have a forged hip stem, we're going to have increased strength. This should be part of your engineering report. Definitely a good question for exams. I would say I put this in the exam 50% of the time. Okay, casting by definition is the solidification of molten metal. If you melt chocolate and allow it to set, that's casting. We've talked before in other videos about how this number should go 1, 2, 3, 4. We've talked about we've seen videos of this dendrite formation. But what we're interested in is these ingots. Now, I'm sure I talked about this on Zoom as well, but I'm going to go through it again now just because it's nice to have a video that people can watch later. That with casting, we can get different kinds of grain structure depending on the conditions. If we have sand, that's going to allow the thing to cool more slowly. We're going to still have some rapid heat loss. So the rapid heat loss creates these column-like or columnar grains, right? Whereas the inside creates small equiax grains. If we have metal, on the other hand, right, if we have metal walls, we have really long finger-like or column grains. Now you can see the sand on this side, because it's cooling slowly, it doesn't. We don't get an equiaxed. Sorry, we don't get the column-like grains in every direction like we do here, because this is sand. In which case, the heat is going to transfer so quickly that we're going to have long column-like grains. I would normally in class show you a whole bunch of those ingots, but we don't have them. In the video we talk about inclusions, so we can have either sediment, where sediment gets stuck here, or we can have voids, where we can have holes in our cast, which are called pipes. A primary pipe is this hole here. A secondary pipe is where we have a bubble that gets trapped inside the metal. It should be important that without reading this, I'm like, why doesn't this one get a label? And that's because it's sediment. That's gunk that's got trapped there, and that's no good either. Okay, so I go into a lot of detail in the video about sand casting and investment casting. There are lots of other kinds of casting, but they're the ones that I am most concerned with. We have 2 different kinds of die casting in the Year 11 textbook, but really the thing I'm going to focus on is sand casting and investment casting. They're the 2 that we need to talk about. In terms of metals, we've already talked about how I've shown you the metals unit and all of our stuff on stainless steel. Titanium, I've already set for homework, and I've given you the notes, and we've already answered most of those questions. The few questions I haven't answered, I expect you to look up using just Google searches and applying your own knowledge. If you have questions, you can let me know tomorrow when I do a Zoom lesson. For polymers, so they talk about ultra high molecular weight polyethylene, right, which is used as the lining in the knee joint. You should be aware of that because that's part of your biomedical engineering report. Ceramics are also discussed. Now, cracks are a real problem for ceramics. It definitely have created a lot of anxiety in my life that I get cracks in my walls. A lot of stress for several years worrying about that. But at the start of this video, when we were looking at the engineering report, we talked about alumina and zirconia. Now, alumina we like because it's a bioinert material. It means it doesn't react with the body. Your body doesn't start trying to treat it like an infection. It's very stable in body, has good compressive strength and high wear resistance, but it suffers risk of fracture. So alumina can be used in dental, like for filling in cavities, and for the femoral head or the ball in a hip replacement. Now, what we can do is we can stabilize it with zirconia. So what zirconia happens is that the example is we can take a cup of tea, and if you heat up a cup of tea in the microwave, you can actually get to the point where the internal temperature is greater than 100 degrees. Now, ordinarily, if you boil water and you get it to over 100 degrees, it will begin a phase transformation and it will start to become gas. But if you microwave the water, you can actually create enough heat in the water that it's not in a stable state. There's too much energy for a liquid state. So what you then do is if you put a teaspoon to start stirring the water, it suddenly that creates a catalyst for the transformation of that change of phase. And you can have a, not quite explosive, but you can have a violent reaction as suddenly all of that water that is superheated changes phase. Well, it's a bad analogy because it's not really in any way the same concept, but I think it's the closest thing that you might maybe deal with in your day-to-day life, which is that you can have partially stabilized zirconia, right? So you can have zirconia in an unstable phase, right? Metastable, where you can squash it into a formation that is taking up less room than it really wants to for the temperature and other pressure conditions. And so what happens is when a crack forms, it can release that extra energy and it can fill up the crack. And so by filling up the crack, it reduces the voids and it stops crack propagation. Now, generally, when we talk about preventing crack propagation, and we'll talk about this next year, when you start to see cracks, what you do to stop cracks spreading in engineering context is you drill a hole at the start of the crack, and that makes it harder for the crack to spread. But that's the advantage of using zirconia in alumina. So alumina has good properties, and zirconia can help us to improve the properties of alumina. So I didn't really talk about polymers very much. I mean, Copeland's only given a paragraph. I'm expecting you to research that. And so what we've now, as far as I'm concerned, discussed that. I'm going to start setting you, next week I'll start setting you these questions for homework. I don't think there's any questions on polymers in the chapter review questions, but I'll have a quick look. Okay, what is the reason for using polyethylene? What is the reason for zirconia? So questions 18 and 19. So there we go. Chapter review question 18 and chapter review question 19. Okay, so nobody asked me to extend the date that I'm going to make the casting video due. I'm going to make the casting video due in... Oh, maybe I haven't been recording for as long as I thought. Does OBS give a counter? I didn't record. That's a shame. Because on Tuesday things start later. Anyway, we're getting pretty close. I've nearly finished what I wanted to talk about. So I've made you do titanium homework, so that's covered. Polymers and ceramics, I will just make you do those 2 chapter review questions, and we're discussing the engineering report. Now, what's really important is discuss emerging, I've left this right to the end, but you can, hopefully the fact that it's in bright red will help people. Discuss emerging technologies used in biomedical engineering materials. Now, we've talked about a whole bunch of engineering innovations, right, recent technologies, but in materials is a bit tougher. So the obvious thing, I mean, these days 3D printing is coming up on like 10 years old. I mean, it's obviously a lot lower, but just it was a widespread, readily available thing for at least 10 years now. So what we consider innovations is often quite difficult for a high school teacher because by the time we're aware of it, it's already kind of out of date. But 3D printing of organs is still it's still a work in progress. It's something that people are talking about rather than where we currently are. We can look at the miniaturization of electronics components as things get smaller and smaller. We can talk about nanotechnology, so using things like graphene is, these are things you're going to have to research yourself, but graphene in biomedical innovations is a consideration. We're using wider uses of carbon fiber, but I mean, carbon fiber is very old technology, just we're using it more and more these days. And then technologies like Neuralink. So that's really a technology, not a material, but I did have Neuralink here. That Neuralink is possible because of improvements in materials technologies. So, the other big one I wanted to talk about is battery lives. So as batteries get better, that it definitely improves what we can do with some technologies. So with prosthetics, for instance, that require electricity to operate, battery life is a consideration. They're the main areas that I can think of. So I've put that in as a question. I've chucked that into the homework I set for you guys yesterday. We've now fully discussed this, especially with the HSC questions I've given. I'll post those to the chat. I'm going to put the casting video is already on YouTube. I'm just going to set that for homework now. I haven't typed up the homework, but it's going to be, the homework will be describe the sand casting. Yeah. Describe the process of sand casting and investment casting. Investment casting you have to talk about as part of your engineering report anyway. And then I will say compare the crystal structure of sand casting versus a material that has been cast with a sand mold compared to the crystal structure of something cast with a metal mold. So die casting, something like that. Okay, with that, I have covered the chapter. I've covered a lot of the chapter. We're now up to electronics and communications. The communication stuff I think we've done. I just haven't ticked it off yet. But tomorrow I will be spending time answering questions. I'll probably allow 30 minutes per class in Zoom, and I'll just spend the rest of the time setting up some resources. See you. Have a great day, everyone.